one thing we need to mention is that limits of exponentials. So for that we have two situations. So when you realize that when b is positive, your graph is always gonna look like this. It's always increasing. It's always above the x-axis. The characteristics of positive base is always results in that graph. So here, when x goes to infinity, when you have larger x, you realize y also goes to infinity. For this reason, when x is infinity, the limit is always infinity, because it's always increasing. When x is going to negative infinity, if you're going this side, then you realize that your y value is getting close to 0. It's never there, but it's super close to 0. For that reason, the limit is always 0. If you consider the graph where b is in between 0 and 1, or in other words, you have a function that is looking like b to the negative x, you're always going to get a graph that looking like this. It's like symmetrical with the previous one. And then here, when x goes to infinity, realize the limit value, the y value, is getting close to 0. And then when x goes to negative infinity, here on the left hand side, the function goes to infinity. So we're going to keep that in mind. So here I illustrate this on an example. So the example is 2 to the x minus 1. So what I can do here is I'm taking the limit, x going to infinity. I'm going to rewrite this 2 to the negative x just so we see it more conveniently. So because it's a negative exponent, I'm gonna write it as 1 over 2x. And then now I can rewrite that 1 over 2x as something like 1 over 2 raised by x minus 1. So you realize that this is an exponential function. Because this is a negative exponent, as x goes to infinity or positive infinity, the values are always going to get close to 0. So limit of that, limit of 1 over 2 to the x as x going to infinity is going to be 0. And then if you separate this with limit of 1, x going to infinity, so this guy is always going to 0. And then limit 1 is always 1. So therefore the result is negative 1. I'm gonna briefly mention some of the applications of exponential functions because I will be recording a separate video for specifically talking about applications of exponential functions. So we know that exponential functions frequently used in mathematical models for situations in nature and society, and when we try to explain things. Some of the examples include things like, bacteria population in biology research, or human population in society or social sciences. Exponentials are frequently used to model those situations. A recent example that I wanted to bring up is some of the models healthcare officials have been using to examine infection rates for COVID-19 is actually exponential. So you may hear on the media, on the news, that people always say things like, oh, it's an exponential model, it's an exponential growth. What they actually say is they actually mean this mathematical model, exponential functions. One model that I wanted to bring up is healthcare officials in Italy modeled the infection rates in Italy, the COVID-19 infection rates, and then they realized that it's actually modeled as 2.6 to the t, where t represents every 5 days, and what 2 to the 6 is this is basically the base constant, and what that means is it's actually every one person infects 2.6 other person per 1 t, where t represents 5 days. In other words, every person in Italy, every infected person infects 2.6 other person in 5 days. And this was a calculation Italy has been using to model their infection rates. One more example that I wanted to bring up for exponential functions is compound interest is exponential. You may have seen this before. I'm not gonna do an example on this, but just thought that it would be an interesting example where you have interesting amount. If it's a compound interest, you have some principal. It's like a down payment you put. So 1 plus R is the rate, N is interest, like interest number of interest applied, and then T is time period. So you guys notice this whole thing is an exponential function because P, R, and N, P, R, N are just constant numbers, but T is a variable. So it's something raised by a variable, right? It's this parentheses raised by a variable. So it represents an exponential function. All right. So next, I would like to mention natural exponential function. One mathematician, Bernoulli, back in 1600s, realized that there was a special case for f of x equals b to the x when the base value b is equal to e, which is approximately 2.719. And that resulted in very interesting developments in mathematics. And for that reason, we commonly use the natural exponential function. So when I say natural exponential function, I always mean f of x equals e to the x, where e, I know, is a number 2.71. The graph of e to the x always looks like this. It passes to the 0, 1, goes from left to right. It's always increasing because the base is a positive number. It's bigger than 1. And yeah, that is what we call natural exponential function. So what I'm interested in next is 1, derivatives of exponentials, and 2, integrals of exponentials. In other words, the rest of the slides will be about the calculus of exponentials. So I'm just going to give you the formula. So d over dx of b to the x is always ln of b times b to the x. So the derivative of an exponential function is by basically itself times the ln natural log of whatever b it is. So you just multiply those things. And ln b is always some kind of number. So you just need to calculate it. Sometimes you can just leave it as it is, but it is basically something to be calculated. Special case, when you have natural log e to the x, the derivative of that is same rule applied, ln of that base, which is e in this case, because here you find the ln, natural log of the base b, here ln e, and then we know ln e is always 1. So you do ln e times e to the x, which is basically e to the x. So one thing to note here is the rate of change, or the derivative, of any exponential function is proportional to the function itself, because you're multiplying by this ln, and that makes it proportional. So the rate of change of an exponential function is always proportional to the function itself. I'm going to take a look at some of the examples here. So for instance, if we were to calculate the derivative of 5 to the x plus sine x, what we would do is we would say, okay, well, I need to find the derivative of this first term, 5 to the x, and then add the derivative of the second one. And then I would say, well, the derivative of 5 to the x, according to the rule, is always ln 5 times itself, which is 5 to the x. And then you would say plus the derivative of sine is cosine. And then that would be a result. And then I generally am okay with leaving ln 5 as it is, but you can feel free to calculate what exactly value that is. Another example I have is d over dx of e to the x, x to the 5. So you realize these two are multiplied, So I have to use the multiplication rule. So I'm going to do derivative of the first, e to the x, times the second term, plus I will do the first term times the derivative of the second. Multiplication rule. So then derivative of e to the x I learned is just ln e times e to the x times x to the 5 plus e to the x, derivative of x to the 5th is basically 5x to the 4th. Realize ln e is always 1, so I'm just going to say e to the x, x to the 5th, plus e to the x, 5x to the 4th. And that would be a result. If you would like to make this a little bit cleaner, what we can say is like you take out the e to the x and then leave it as something like x to the 5th plus 5x to the 4th. That would be a very reasonable answer. So now we take a look at how to integrate exponential functions. So the way we integrate them is we take the integral b to the x dx. It's always b to the x over ln b plus c. And you realize ln b comes from what we just had because the derivative of it is ln b times that. So integral of it must be the reverse order. So you, instead of multiplying by ln b, you divide by ln b. Special case for it is e to the x. So e to the x has to be e to the x divided by ln e. You realize ln e is always 1. And for this reason, the integral of exponential function is basically itself plus c. A couple of examples for this is given. So if you were to integrate -1/2 times 5 to the x dx, we could do this as following. Because this is a constant, I can take it out. I can say 1/2 integral 5 to the x dx. And that is basically 1/2. So antiderivative for 5 to the x is basically itself divided by ln of that base, which is 5. And then you add c. So if you clean this up a little bit, you can say 1/2 ln 5, just some number, times 5 to the x plus c. That would be a very reasonable answer. One more example at the bottom. Integrate 2 minus 3 times e to the x dx. So because there's the subtraction, I can write it in different integrals. So first integral will be 2 dx minus integral 3e to the x dx. I can split this furthermore because 3 could be taken out. So integral 2 dx minus 3 times integral e to the x dx. 2x results in, or integral of 2 results in 2x. And minus 3 times integral of e to the x dx is itself. So you're just going to say e to the x. And then at the end, we just add c. So therefore, the result is 2x minus 3 e to the x plus c. And that's going to be all for this video.